Okay, I want you to forget everything you think you know about time. Seriously, we all assume a second is a second, no matter where you are. But what if I told you that on the moon, time literally moves faster? Now, this isn't some sci-fi plot. It's a fundamental problem of physics, and figuring it out is one of the biggest hurdles we face for our future in space.
This number. This is what it all comes down to. 58.7 microseconds. It's such a tiny, tiny slice of time. We're talking less than 1/10,000th of a second. You could never feel it, never notice it, so why on earth does it matter?
Well, because when you're dealing with high-precision space exploration, a tiny difference like that becomes absolutely catastrophic. For a self-driving rover or a lander that needs to hit its mark perfectly, this tiny daily error isn't just a small problem, it's a potential death sentence.
To put it bluntly, time as we know it is just broken on the moon. The system that runs our entire planet, Coordinated Universal Time, or UTC, it just doesn't work right once you get out of Earth's deep gravity well. And this creates a huge, and I mean potentially fatal, problem for something as basic as navigation.
So here's how that tiny microsecond difference blows up into a real-world disaster. If you took an Earth-based GPS to the moon, that 58.7 microsecond drift would throw your location off by 10 kilometers every single day. Imagine you're aiming for a flat, safe landing zone and you end up 10 kilometers away at the bottom of a crater. Not good.
So what is going on here? Why does this even happen? Well, the answer comes from one of the most famous ideas in all of science, Albert Einstein's theory of relativity. It's the theory that taught us that time isn't this fixed, constant thing. Nope, it's relative, and it's directly bent and stretched by gravity. It's all because of a wild concept called gravitational time dilation. It's a key part of Einstein's general relativity, but the core idea is actually pretty straightforward. The stronger the pull of gravity is, the slower time itself actually moves. And this slide just breaks it down perfectly. Earth, right, is way more massive than the moon, so it creates a much stronger gravitational pull. This literally puts a drag on time, slowing it down. But since the moon has only about 1/6 of Earth's gravity, its clocks just tick away a little bit faster, adding up day after day after day.
Okay, so since we can't really change the laws of physics, we have to invent a whole new system. And this has kicked off this huge global effort to create something called Coordinated Lunar Time, or LTC. We're talking about a brand new timekeeping standard, built from scratch just for the moon. I really love this quote from the source material. It just nails why LTC is so important. I mean, think about it. You're going to have rovers from Japan, landers from the US, and satellites from Europe all trying to work together. If they don't have a shared sense of time, they can't talk to each other. LTC is that common language, that bridge that lets all these different machines operate in perfect sync. So, how in the world do you build a clock for another world? It's a massive engineering challenge for sure, but it really comes down to 3 big steps. First, you've got to put these ridiculously accurate atomic clocks on the moon and in orbit around it. Then, you pick one of them to be the master clock, kind of like the moon's version of Greenwich. And finally, you have to use lasers to constantly sync up lunar time with Earth time, just to make sure they stay in a predictable, known relationship.
But look, this isn't just some technical puzzle for scientists to solve. It's also become a major geopolitical issue. This mission to define time on the moon has quietly turned into a really high-stakes race for influence and power as we head into this new space age.
You know, history gives us the perfect parallel for this. Think back to 1884. The British Empire, with its dominant navy, basically got to decide that the prime meridian, the 0 point for all world longitude and time, would run through Greenwich, London. Well, the nation that establishes the Greenwich of the moon is going to hold a similar kind of power for decades.
And right now, we're seeing 2 major groups form. On one side, you have the US-led Artemis Accords, which are all about creating shared open standards for LTC. But on the other side, you've got the joint China-Russia plan for their lunar research station, which could easily create its own totally separate and competing time standard. Whichever group gets to set that standard gets a huge leg up, shaping everything from science to business on the moon. This all leads to what experts are calling the risk of bifurcation. Just imagine a future moon split into 2 competing time zones. A US rover couldn't sync up with a European lander simply because their internal clocks would be fundamentally incompatible. It would make coordinating anything a total nightmare and would seriously increase the risk of accidents. So a single, unified lunar time isn't just for convenience, it's pretty much essential for survival.
Creating a clock for the moon is so much more than just a cool project for this decade. It's a real turning point in human history. It's the very first time we've ever had to create a time system that isn't based on the spin of our own planet. This timeline really puts it all into perspective. Back in the 19th century, we needed railway time to keep trains from crashing into each other. In the 20th century, we created UTC for global communication and travel. LTC is just the next logical step for the 21st century. And really, it's just a practice run for the even bigger challenge waiting for us, creating a time standard for Mars.
And that brings us to this quote, which just gets right to the heart of it. The simple act of creating a lunar clock forces us to change our entire mindset about the moon. It's a huge statement that we're moving past just visiting and planting flags. We're now building the basic, fundamental infrastructure you need to manage a permanent human presence somewhere that isn't Earth.
And that leaves us with this one last, fascinating question. We're always talking about mining for water ice or rare minerals on the moon. But what if we've been overlooking the most fundamental resource of all? In a future built on synchronized robotics and high-speed data, control over time itself might just be the ultimate prize. The race is on, not just for territory, but for the second.